Hi everyone, here we are going to derive the heat equation in one dimension. It is one of the most important derivation in the course of partial differential equation, and here you can see statement before you. Within this statement it says you have a infinitesimal, you have a rod insulated from its lateral edges, and if there is a heat passing through the rod, that it will always satisfy this relation. And this relation is the first derivative of u with respect to t is equal to the constant multiplied by second derivative of u with respect to length with respect to x. And here what is k? K is actually your the constant which is the constant of thermal diffusibility. Now let's start uh, let's start and understand how this equation emerges. Now here is the proof. Within this proof, first you have considerations. You will have to consider a rod of length L and a homogeneous metal of cross sectional area A, which is completely insulated from its lateral edges, and then you consider a very small infinitesimal element of that rod, and you take its length between x and del x, and the main thing you are trying here is to write an equation of conservation within that area, within that infinitesimal area. What is visualization? What's happening here? If you are interested to see, then you have a rod here. Sorry for the bad drawing. I don't have any scale in drawing. So this is an infinitesimal rod, and this is its length, which is L. Here is an area, which is A, and any other thing? Yeah, if your length will be 0 here, x represents the length, and length will be L here. And now you will suppose so let's, if I can change the color. Okay, yes. So here you have an area in infinitesimal element of the rod here. Again, a cross-sectional area will be A here, So, and your x will equal to x here, and you can just take x, and here it will be del x. Now, heat is moving from here to here, so it will be it will depend on the length and on time when it will move from here to here. But when heat will go out from this side, you will have x plus delta x. Here it will depend upon this amount of length and time. Now this is an idea what's happening here. Now let's see what data we have here. We have a change in volume del V, which is this is the volume of the element, and this is equal to volume is volume is actually area multiplied by length, but length is changes, that is why. And here A is the cross sectional area of the, sorry for this, cross sectional, we can say area of the element. This time it's element. And change in mass, this is mass of the element. Mass of the element, and mass can also be written as a product of density and volume, is area, a product of area and length. Here length is changing, so change in length, or you can write change in volume. So from these things, okay, the color is good because we are just focusing on the infinitesimal element, and infinitesimal element was represented by red color, so it's good. But now here a thing is changing here. Now you're considering a different thing. You say the amount of heat at time t can be represented by a principle, a flux, the amount of heat okay, so at time t is, according to the formula of flux, you can write like dependent at t and this, your heat is always equal to this. Okay, and from the above data you can say from the above two equations, from the above data, from the above data you can rewrite this same equation as q x t delta x equals to, actually you are aware of the change in mass, so now if I substitute the value of change in mass, this is delta x, and you got a new equation. So you here you also remember the rate of change of heat. Okay, this must be capital. The rate of change of heat is, it is always change with respect to time equals to C rho A area, change in length, and again a derivative in which u is dependent on x and t, and derivative of u with respect to time. So this is another principle which we are considering here. And now you also consider heat flowing in and heat flowing out. Okay, what's going here? Actually, there are a lot of rules for heat which are followed when heat moves from a metal. What we are doing, we are assuming our data and we are trying to follow those 3 to 4 or 4 to 5 rules, and by analyzing our flow of heat according to those rules, we will end up with an equation, and that will be the equation of heat flow. That is a little bit different sort of derivation here. So it's not like the derivations of algebra, so you might feel it a little bit different. So here you see we have took heat flow in and heat flow out into our consideration, and from all of this above we are also going to consider the principle of heat conservation by the principle of heat conservation. What is the principle of heat conservation? The rate of change must equal to the rate at which heat is flowing in subtracted by, or you can say is lesser than the rate at which heat flows out. This is the rule. So here you can see the principle of heat conservation says that the heat within a rod is always the heat in subtracted by heat out. You can, okay, in other words, you can write heat in it must always be greater than heat out, or yeah, this is going to be an equation like you will write dq over dt, in which this is now according to your consideration, according to your own model, your heat in is this one and your heat out is x plus delta x and t and then a. So according to your model, your equation for the heat conservation is this one. Now you can you can take a as a common because cross sectional area is constant, so you will have qxt minus q x plus delta x and then t here. Now in our data we know about this side from the for the left hand side we are aware of it. You can see here we have, here you can see we have the change in heat. So if we substitute this value into our new equation, into our equation of heat conservation, we will end up with a new condition. So let's write it here. You can write substituting the value of dq by dt, the value, or you can say the available value of dq by dt in this equation, in the above equation, you will have c rho a change in x equals to, okay, not this, still you have a partial derivative of u with respect to t, and your u is dependent on x and t. This is t, and this thing is equal to your right hand side, which is qxt and minus q x plus delta x and t. Now you can here you can cancel this a with this a, and no other thing can be cancelled, so rewrite a new equation here. So the new equation will become c rho and delta x, I am moving this delta x on the other side, so you will have x t here divided by delta t, which is equal to q x t minus q, here you have x plus delta x and t, and this whole thing is now divided by delta x. And you must know that this right hand side is going to, if I apply the limit, if I apply del x approaches to 0, I will have the definition of derivative on the other side. Let me tell, okay, taking the limit del x approaches to 0, we get delta u x t divided by delta t equals to, now you have a limit here, limit delta x approaches to 0, and the other thing was xt minus q x plus delta x then t divided by delta x. So if you remember the definition of differentiation, then this right hand side becomes the partial derivative of q with respect to x. And here if you introduce Fourier's law, then it will complete your derivation. Now by Fourier law of heat conduction, in one dimension, you can write q xt, sorry, this is your actually law of heat conduction. You are nothing, this is a universal rule, you are not doing anything here. So from this rule, you can say from the above two equations, what you can conclude that this u x t divided by delta t equals to this kappa, and second derivative of u x t divided by the second partial derivative of u with respect to x. And now if you rearrange this thing, you will get this thing here divided by delta x squared, and this is equals to 1 by kappa, and xt divided by delta t. So you can see this is your heat equation. You can write thus: heat equation in 1D is partial u, second derivative of u xt divided by with respect to x equals to 1 by kappa. Okay, again the partial derivative of u with respect to t, and here your k is where this k is actually the previous k divided by c rho. You can put this a slight notation here to stay away from the confusion. This was kappa, and the new k is your constant of diffusibility. So this is your derivation of heat equation. You must know that it is done by considering a lot of principles of heat which the heat follow. Those principles are considered, and you also consider an infinitesimal rod element of the rod, and then you take all the data into your consideration and all of those rules, and by following those rules you end up with this equation, which is said to be which is called as the heat equation in one dimension. Thank you.